Good day, everyone. We are going to present brain tumor image classification from MRI using data mining techniques. And we are from Group A, and our team members Liu Yiting, Hemasri, and myself, Prema and Sharwani. Let's begin with the introduction. Brain tumors are very serious and need to be diagnosed early for better treatment. MRI scans are commonly used to find tumor, but reading this image manually takes a lot of time and can lead to mistakes. Our project focused on using machine learning to help with this problem. We tested three models: CNN, SVM, and random forest. CNN is good at learning features from image automatically. SVM works well with smaller dataset and helps separate different types of data. Random forest combines many decision trees to make predictions. We used a dataset with MRI images labeled as either tumor or normal. The images be pre-processed and tested using different training and testing ratios like 30 to 70% and 70 to 30% instead of regular cross validation. Our aim is to see which model gives the best result based on accuracy, precision, recall, and F1 score, and also ROC AUC. We also want to find a model that not only performs well but can be used easily in real hospital to help doctors make faster and more accurate decisions. Let me pass it to other teammate to more explanation. Thank you.
I will represent the related work that forms the foundation of our research. Many recent studies have explored hybrid techniques combining convolutional neural networks with traditional machine learning classifiers, such as support vector machines and random forests, for brain tumor classification using MRI images. So let's go over a few um, key studies highlighted in Table 1. First, by Mishra, they propose a hybrid model that uses a VGG-based CNN for feature extraction, followed by an SVM classifier with RBF and linear kernels. They achieve impressive accuracies of 98.18% and 99.78% on the two binary MRI dataset. Next by NASA, this study compared random forest and CNN-based approaches using a large dataset of over 3,000 MRI images. They use GLCM and LBP for handcrafted feature, followed by PCA for dim- uh, dimensionality reduction. The RF model achieved 91.95% accuracy, while CNN variants reach around 87.9%. Okay, following by Rasul, they fine-tuned GoogleNet for feature extraction and used SVM as the classifier. The model achieved 98.1% accuracy with 98.2% precision and 98.1% recall, showing a strong performance across multiple metrics. Following by Moldovanu, this study will evaluate several hybrid models, including CNN-RF, CNN-SVM, and Efficient Net Bio SVM. Among these, Efficient Net Bio SVM achieved the highest accuracy of 99.5%, followed by DenseNet 169 SVM at 98.6% and CNN RF at 97.2%. The next one is by Koramipo. They developed a multi-path CNN architecture where the traditional softmax layer was replaced with an SVM classifier. They mod- their model achieved 98.3 accuracy on the Figshare dataset, and 98.2% on Kaggle, and 99.1% on a combined dataset with F1 square scores and sensitivity all above 97%. Finally, by Hafiza Akhtar, they compare four models: CNN, Inception V3 based CNN, CNN RF, and CNN SVM. Among them, CNN RF achieved the highest accuracy of 96.5%, slightly better than CNN SVM, which reached 95.4%. As we can see from these studies hybrid model, particularly those combining CNN with SVM or RF, consistently yield high accuracy in brain tumor classification tasks. This finding reinforced the effectiveness of integrating deep learning with traditional classifier in medical imaging application.
Alright, thank you. Next, I will present my part, which is methodology. So, as the study employs a supervised classification approach by using Python software, and it helps us to detect the brain tumors, which is our selected dataset for this project, for the MRS. And the classification task is in this study is a combined binary classification of the images that represent both a tumor and normal. And this methodology of a project is consists of five major steps, which is the data collection, pre-processing, feature extraction, model transition, and evaluation. So next, I'll proceed to explain these five major steps. So first of all, the data collection, the first step from the methodology. And this data set is a combined brain MRI data set that we chosen from mainly data desperately, and which is consist of 3,992 JPEG MRI images, and which is divided for both part, which is for tumor class and normal class. As we can see, show data of the collection of total 1,167 for tumor class, and for the normal class it consists of 1,725 images. As this data is completely organized in two separate folders for each class to distribute the difference of the images, which is classified by using a 2D grayscale, which is telecasting the real MRI scans to make it as a flexible data set, as it will be applicable for our binary classification to make up in this medical imaging of our project. Next, second step is pre-processing. So as these processed images are were obtained using by image data generator from the TensorFlow Keras library, and were like standardized and prepared for data processing. So the following steps were adopted, which is like resizing all the images for particular allocated sizes, like for example 224, which is a standard sizing of the images to visualize the correct VVGG16 model. Next, moving on to the class balancing. So to ensure the model was will be biased and to like have the same result, to obtain the result equally, we decided to balance the class randomly with normal and tumor dataset, as we can show the equivalent dataset. And here I have provided a table to show a view clear representative of the equalization data, which you can see here as the original count and differentiate with the final count. So we decided to go with the 1,467 counts, as it will be equivalent and representative of the fellow both datas. For the feature extraction, like different feature extraction will be applied in our project, which is CNN, SVM, and RF. And the last step from the methodology is the model training. So here we decided to go with Python, as it is used to train three classifiers through different data splitting, and the ratios to include the k-fold cross-validation terms. So the performance was kind of stability and helpful, as it was tested by using three different separate ratios such as 70-80, 80-20, and 60-40 splits. And moving on to the main dataset, as I explained earlier, so dataset is a study that we search from the brain MRI dataset, and which was conducted and searched from mainly data source. As the dataset has a variety of numerous accounts data, the 2,934 grayscale images, as half of them from the normal, which is consists of 1,467, and the remaining are from the tumor, which is 1,467 as well, to show a balanced data set. Here, I would like to show the represent data which I explained earlier. As we can see here, I have shared the figure 1, which is the normal data set, and figure 2, it's a tumor data set. Alright, next we'll move on to algorithms. So here the three follow algorithms were used in the study, which is algorithm 1, convolutional neural network CNN, algorithm 2, support vector machine SVM, and thirdly random forest RF. So as we can see, for the CVM algorithm, we decided to go with dataset as it helps to conduct a deep learning that extracts the special features automatically using the convolution laser. To represent the choice, I have included the formula, which is example 1 that I attached here, where the input image will be conducted with filter weights or the convolution without the bias or the sigma activation function. Next, for the SVM sector vector machine, and which decided to go with this because it finds the best separating hyperplane for binary classification. As the formula shown earlier, is also representing the objective function to equalize the subject to contact a regularization parameter as well. As for the third random forest algorithm, is an assembled classifier that builds multiple decision trees and uses majority voting to provide a decision final modularized conduction and decision. Alright, next I will present the last part of the methodology, which is the evaluation matrix. So here, same as algorithms as well, we decided to go with four types of evaluation matrix that will suit be our project. As first of all, accuracy, precision, recall sensitivity, and F1 score. So for accuracy, it's like a proportion of total correct prediction, which is shown in the formula below. It will directly show off the proportion that needed for the total to conduct the prediction that our data needed. And secondly, precision. So precision is the proposition of a correctly predicted post-it interfaces to conduct instance result. And for the recall, which is also known as sensitivity, this is because it recalls the measure to conduct the ability and identify the positive inset at the time of beginning. And last but not least, the F1 score. It is to maintain the harmonic mean of the both precision and recall. And here are the formulas that I attached earlier for all the representative of the relation matrix. So that's all from me. Thank you.
Next, let's come to the result part. This table has shown the overall result trained by different algorithms, which are convolutional neural network (CNN), support vector machine (SVM), and random forest. Now let's analyze each evaluation metric in detail. CNN shows the highest and most consistent accuracy, improving steadily with more data up to 98.86%. SVM follow closely, nearly matching CNN at higher speeds. RF lags behind throughout in these accuracy evaluation metrics. For precision, SVM and CNN achieve very high precision, which is up to 99.31% at larger splits. Random Forest starts strong but does not match the top-tier performance of CNN and SVM. In recall, CNN maintains the highest recall overall with 98.41% at 70-30 split, excelling in identifying true positive. SVM performs well but falls short at small splits. Random Forest has the lowest recall, especially with smaller datasets. For F1 score, CNN consistently leads with a balanced F1 score, peaking at 98.986%. SVM remains competitive, while Random Forest is stable but lower. For AUC-ROC, all models show strong class separation where R greater than 0.92. CNN reached near perfect discrimination, which is 0.9998, followed closely by SVM and RF at higher speed. Now let's come to the discussion. First, CNN or convolutional neural network shows the best overall performance. It achieves 98.86% accuracy with 99.31% precision, 98.41% recall, and an AUC of 0.9998. It's highly consistent as we increase the dataset size and is ideal for tasks that demand high accuracy, strong recall, and excellent class separation. The main drawback is its high computational cost, making it less suitable for real-time or resource-constrained environments. Next,
SVM or support vector machine also delivers high accuracy and precision with an AUC of 0.9995. However, it tends to have weaker recall at mid-level data splits, meaning it might miss some positive cases. It's a lighter model computational and it's well suited for precision-focused tasks where speed and resource efficiency matter. Lastly, random forests show moderate performance, with accuracy starting at 81.4% and improving with more data. It handles mixed data types well and is easier to interpret. That said, it still lags behind CNN and SVM, especially in precision and recall, so it's less suitable for the tasks that require high classification performance.
Let's now look at table discussion, which compare our experimental result with previous studies on brain tumor classification using MRI data. In our study, we tested three models as CNN, SVM, and random forest using binary MRI classification. The CNN model showed the strongest performance with an accuracy and F1 score of 98.86% and a ROC-AUC of 0.9998. This indicates that our CNN model is highly consistent and accurate across all evaluation metrics. The SVM model, while slightly lower, still achieved 98.75% accuracy and 0.9995 ROC-AUC. It showed high precision but slightly lower recall compared to CNN. The random forest model recorded a respectable 97.95% accuracy and a ROC-AUC of 0.9997, indicating strong conservative performance. When compared to other related work, first by Mishra, they achieve up to 99.78% accuracy using VGG-CNN and SVM hybrid, but this way on a simpler binary classification task. Next by Raman, they use GoogleNet and SVM on a 4-class MRI dataset and achieve 98.1% accuracy, showing the strength of multi-class performance with deep learning. Following by NASA, they use RF and CNN on a larger multi-class dataset, but RF only achieved 91.95% accuracy, showing that our RF model performs significantly better. Following by Moldovan reported the highest accuracy of 99.5% using EfficientNet Bio (SVM), which is a hybrid deep learning approach. Lastly, by Munira, they use CNN hybrid and achieved 96.5% accuracy, slightly lower than our CNN model. In summary, our study confirms that the standalone CNN model is extremely effective for brain tumor classification, outperforming several hybrid approaches. SVM and RF also offer reliable alternative, especially when we need to consider simpler or more efficient implementation.
So, as for the conclusion, this study used MRI images and data mining technique, which is CNN, SVM, and RF random forest to classify brain tumor types. CNN achieved the best performance with 98.86% accuracy and 0.9998 ROC AUC, outperforming SVM and RF across all metrics. SVM and RF also showed strong results with SVM slightly lower in recall and RF being more stable but less accurate. The conclusion is CNN is most effective model for brain tumor classification, especially for high precision applications. Future works use larger and more diverse dataset for better generalization, apply data augmentation and dense to handle the class imbalance, explore transfer learning with models like ResNet, DenseNet, and EfficientNet. Develop hybrid models, for the example, CNN with SVM to combine strength. Deploy models in a real-time diagnosis with tool for clinical use. That's all from us. Thank you.